Okay, so what I'll do real quick is just a quick video going over more of our finite automata, this time doing differences between our NFAs and our DFAs. So that's going to be dealing with conversions from them and then just other variances between them. So I'm just going to take a look at the slides real quick. Now, this is going to be a fairly lengthy one because this NFA is the exact same as this DFA. And it's possible to convert any NFA to a DFA counterpart, but it is a lengthy process doing so. And before we can really do that, we need to look at the difference in the definition of an NFA versus our prior definition of a DFA, which is one very key difference. So we still have that same 5 tuple from earlier that has our states, our alphabet, our transition function, that has a transition table in it, our start state, and then our set of accept states. The primary difference is this right here. This is a cross product of the alphabet with a subscript of the epsilon that indicates P of Q. So the primary difference there is the fact that we need a power set of Q rather than the set of Q itself, because we need every possible combination to derive that proper non-deterministic branching state that we can get. And the other little small difference here is instead of having just sigma here, we have to union it with a single character of epsilon to add that to the actual alphabet, because our NFAs have epsilon as possible inputs and whatnot, so we need to actually take that into account when deriving our transition function. Those are the only differences. Everything is the same sans those aspects, but those two small little differences in the definition go a very long way when it comes to actually making those conversion processes. So if we look here, then we have a pretty simple NFA here, my bad, and its corresponding transition table down here. And as we know, we're able to go to multiple places from any state in an NFA by using the same input. And we can see that in Q1 right here. So Q1 on a one input can either go to Q1 or to Q2. And if we look over at our table, we can see Q1 on a one input, it has the set of Q1 and Q2. So our transition function here, our transition table, will be derived of a set of states per transition rather than a singular state, where DFAs are guaranteed to only go to one state on a input. The NFA, on its non-deterministic nature, can go to a set of states. And also it can go to a null state, which is not going to be present because we just don't write those out in NFAs. You'll see that this becomes its own actual state when we do the DFA conversion process. So if it doesn't go anywhere, like if we go to Q1 and try and do epsilon transition, there's nothing there. If I go to Q2 and try and do a 1 transition, it only has 0 and epsilon. It doesn't go anywhere. Remember, that state of the branch in our non-deterministic trajectory would halt there essentially. So it basically uses a null state to determine that there is nowhere that this state will go to on this input. We just don't actually write it out in the state diagram because there's no reason to in an NFA representation. And if we look at the overall definition, here's our NFA. Here's the actual 5 tuple we're trying to derive. We have our 4 states of Q1 through 4, right here. Our alphabet of 0, 1. Those two here. Remember, when we actually do the transition function, we add epsilon to it. And then our start state here is Q1. And our accept state is just Q4 by itself. So that's the whole formal definition for that particular NFA. And every other NFA will also follow this process as well. So we also have that same 3 condition requirement when we are recognizing languages for NFAs, just like we did back with DFAs. And the first and last one are identical. The only difference here is rather than using strings of W directly, we now have a Y in this case. So W equals a concatenation of Y1, Y2, Y3, etc., where each YI is a member of our actual alphabet. This is a means to try to encapsulate all those non-deterministic branches that are happening when you do NFA. So the strings, while they do accept them and recognize them, it is a much more broad scope of what is actually being recognized. So basically the three portions here has a start state, has some strings it's going to accept that exist inside of its alphabet and whatnot, and then also a accept state at the end. Those are all basically going to be similar to our DFA process. And the actual lengthy process when it comes to this is when we convert our NFAs to our DFAs. That is a potentially lengthy process, but it's really going to be more apparent as we recall what a power set is. And essentially, when we look at cardinality of what the DFA and NFA require. So NFA just basically needs its states and whatnot. But when we do the conversion process over to a DFA, now we need a combination of every possible state combination there is. So if we have 3 states, then we are going to need up to 8 states in our DFA. So let's say I had 3 states here in my NFA. Well, if that's 1, 2, and 3, there are going to be up to 8 ways that I can represent this. And that does include the empty language and everything, because, you know, the power state can have an empty set inside of it because the empty set is a subset of all sets. And then everything else is just 1, 2, 3, 1, 2, 1, 3, 2, 3, and then 1, 2, 3. Those would be all the actual states we can have. You can see that represented right here in this list. So again, null 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Again, this is all using roster notation, so the order of the actual sets here don't matter. So this is going to be the NFA we're using for the entirety of the rest of this slide set. Our whole goal is we want to convert that NFA right here to its DFA counterpart. And it's going to have 2 different endpoints essentially. One that is the full breadth of all of these states here in the power set, and then one that is going to be a simplified version because we're not going to need every single possible combination. Recall in the previous slide I said it's going to be up to 8 states, but not necessarily exactly 8. So first things first, we get all of our actual possible states. We have all 8 of them right here. That's the first step. So from there, we identify our accept states. So combination states encompass all the listed states and their transitions, so we will treat them as such. This also affects what is and what isn't regarded as an accept state. If we look at the actual NFA up here, our accept state is state 1. So any state that contains a 1 in it does include that state by itself. So if we end on one of these 4, it would accept. And then we'll just go through this actual process here and slowly accommodate each possible transition. So next we can add the transitions from the state of 1. Again, this is just 1 by itself. We do not mark our epsilon transitions. So 1 by itself on an A input, it doesn't go anywhere. So we are going to send it to our null state. So again, here's our DFA. We actually have a representation of the null state itself. And then if we do transition to B, it goes to 2. 2 by itself, that's the only place it goes to. So there's our first step. Next we would do 2. Let's go ahead and mark those. Alright, so if I'm looking at 2, we have our first instance of going to multiple states. So 2 on an A input can loop back to itself, or it can transition over to 3. So instead of going to 3 or going to 2, we are going to send it to 2, 3. So it goes to its first combination state. On a B input, it just goes 3 by itself. So we send it over to an isolated 3. Next, we'll work on 1, 2 actually, just because it's a combination of these. A little bit easier to write this out. So 1, 2 is essentially at both states 1 and 2 simultaneously. So this is where things can get a little bit weird. On 1, 2, if I'm looking at where does 1 go on an A input, I kind of already looked at that earlier, goes to a null state, but 2 on an A input goes to 2 and 3. So when I look at both of these at the exact same time, my possibilities of going somewhere on an A input is 2 and 3. And then if I look at this, when it comes to looking at 1 and 2 simultaneously, where do B go? Well, if I'm at 1, B goes to 2. And if I'm at 2, since again we're doing 1, 2, B goes to 3. So I can go to 2 and I can go to 3 because I have this B input from 1, this B input from 2. So regardless of A and B, 1, 2 goes to 2, 3 regardless. So that's what we're going to mark. And now look at 3. 3 goes back to itself in an A transition due to the epsilon transition from 1. And if I look at that, A transition goes to 1, loops back to itself here. So we end up with 3 on an A input actually goes straight to 1, or it goes to 3 because this is an empty string. We don't mark our actual epsilon transition, so just A goes to 1 and 3. B input, nowhere. So it just goes to the actual null state. Okay, so next one we're going to look at is 1, 3 combination again. So 1 through will always cycle back to itself on an A in transition because again we have this whole cycle here. So if I'm at 1, A doesn't go anywhere. If I'm at 3, A goes to A. But again, like I said earlier, since that epsilon transition happens here, it technically goes back to itself. So it's this self-repeating cycle. So we loop it back to itself. B, 3 doesn't go anywhere on B, but 1 goes to 2. So we will send 1, 3 over to the isolated 2. Next is going to be 2, 3. So it can reach any state on an A transition. So it is going to be our first occurrence that goes to the triple state over here. 1 on an A input, it goes nowhere, right? Again, here, 1 goes to null state, but 2 goes to itself. It goes to 3, and then 3, I don't know why I looked at 1, I was caught here. 2 and 3. 2 goes to 2 and 3, and then 3 goes to 1. So it goes to all 3 of them. And then 2, 3's B. That's just 3. Because 2 goes to 3, 3 doesn't go anywhere on a B input, so send it back down to 3. And then finally our 1, 2, 3 state. Not too surprising, 1, 2, 3 on an A input is just going to cycle back to itself because we already know that there's somewhere that can get to it from A. So since it includes itself, it's going to be able to cycle back. But the more interesting part is that it doesn't cycle back to itself on a B input. That is because there's no way to get back to 1. So 1 goes to 2 on B, 2 goes to 3 on B, but nothing ever points to 1 on a B input. So you can never get to 1 if you pass in a character of B. So this would constitute pretty much all of our actual transition states. Except for, our null state doesn't technically exist. It's just always going to loop to itself because that's basically the point where the actual input process is done. It'll continue to read in inputs because it's deterministic. It has to actually cycle all the rest of the inputs, but we need it to actually be kept in this trap state essentially, because it's eventually just going to read the last input and reject there. You don't see that in the NFA because this state doesn't exist. It just basically halts there essentially. And then finally, again, we need to actually have a start state. And the start state's a little bit strange because you look at it and it's like, oh, it starts at 1. Well, just like earlier, does epsilon exist? So the start can technically be at 3. So start state is 1, 3. And again, that only happens because epsilon does not affect the string that is being parsed, because that is an empty string that's being processed. So I could start at 1 with an empty string, or I could start at 1, use an empty string, which is basically a free transition over here to 3, and I have not changed the actual state of my string whatsoever. So 1, 3 is going to be the actual start state here. And the actual simplification process here is just removing anything that we couldn't actually get to. So if we looked at it, there's no way to actually transition to 1. Nothing was pointing to it. And same thing with 1, 2. Nothing actually pointed to those states, so there's no way to actually arrive at them. You only were able to point to other things, but that's not how things work. So even at your start state, something's pointing to it, and it's basically where we start. And there was never anything that actually cycled back. I'll actually go back to the slide and you'll see there is nothing as an input arrow to this state or to this state. So we would never be able to arrive at those states. So it's perfectly fine if we remove them. Now, that makes things look a lot cleaner because this is more the idea of our finalized state here for our DFA. And again, we have up to 8 states since we had a starting of 3, but we end up with only 6. And one of those is just a null state that we have to accommodate because we're in a DFA. And the idea of just saying there are no inputs at this point doesn't exist. Whenever 3 was here, you have to say B goes somewhere. In the NFA, if you look here, there's just no B transition going anywhere. And that's okay for NFAs. DFAs don't work that way. You have to accommodate every single input in a DFA, so we have to make sure we keep this null state as a means to say, hey, whenever I pass a B, it's just going to go over there, and it will never actually accept anything because NFA would never have that branch in its actual trajectory. So that's the DFA process right there. And again, we only have 3 inputs with 2 characters in our alphabet, not counting the epsilon input when we actually do the process of conversion. That's not very many transitions going on. The one we saw at the very beginning is honestly more complex. It would have up to 16 actual states. We only saw 8 if you go back in the video and look at that. There are many of the combinations of the power set that just will never be able to arrive at there. So that's when we cut out those 2, the 1 and the 1, 2. There's no way to arrive to those states, so we don't need them in the actual end product. So you're going to see that pretty frequently if you do these conversions. Now, transition tables are also going to see a massive benefit for NFAs over DFAs, because the complexity of these tables are going to spike with the number of states that DFAs require. So if we look at this, our NFA only has 3 states, 1, 2, and 3. And most of these actual transitions are null states. So if I go to 1, we do not have a transition on A, so it's null. I can get to 2 on a B input. I get to 3 on epsilon input, so that's it. When I look at my state of 2, if I pass in an A, I get a combination state of 2, 3, which can be a little bit convoluted because again, we have a set of sets, a set of states essentially. But we get to 2, 3, and that's it. Then I do a B input, I get to 3. There's no epsilon transition, so it's a null state. I get to 3. The only thing I can do is get to 1 from A, and then the other 2, those are going to be null transitions, so null states you get to. So that's it. That's the transition table for an NFA. It's genuinely quite simple. The only thing that might throw you off is just this combination, this set of states essentially that you can get to. But as long as you're paying attention, I'm here at 2, count the number of places that A goes to, it goes to 2 and it goes to 3. That's it. That's the entire process there. Now, if we move to a DFA though, it starts getting a bit more complex. So again, we're going to look at the simplified version of this. And now we have the actual null state as its own separate state, because DFAs have that restriction that there is no just drop an input here and don't worry about it. You have to account for that state. So your transition table is going to have that state because in DFA, that state exists. Now we don't have 1 or 1, 2 here because again, this is a simplified one. We don't have those 2 states. And it just carries the same thing, but those combination states are still going to exist. They didn't go away because this was derived from a non-deterministic branch, essentially. It accounts for every single possible combination you can get from the original simplified NFA. It just now makes it deterministic in nature with the fact that we account for every state, and every single one of these states has an AB coming out of it because it needs to account for every single character transition from the alphabet. Epsilon's not a thing, and the actual null states here indicate an actual state. So that simplified DFA is already quite more complex than our previous NFA. And if we look at the actual full complete one, now it's just even more going on here because it now accounts for every single possible state. So we have all 8 of these from the actual power set. And honestly, outside of trying to look at the entire deterministic suite of transitions, it's so much better to just work with the NFA if you have a good understanding of NFAs as a whole. So honestly, this is kind of showing the strengths of NFAs. There are definitely strengths of DFAs for sure. Don't get me wrong. DFAs have their place. They're really, really good in terms of application and making sure that you are accounting for every single possibility at every single state. So if you want something very, very thorough and complete, then having a deterministic variant to really kind of double check what's going on at every single point in your machine, that's really good. But when it comes to doing, a more simplified approach where it's just nicer to work with, especially when we start getting into grammars and languages and regular expressions and stuff like that, NFAs, and especially being able to have epsilon, being able to have multiple trajectories from one state. So if I have one state that has 3 possible paths in the same input, that flexibility is just, it's too good to pass up in certain situations, especially when we get to regular expressions. That'll be the next topic, so we'll get to that pretty soon. Anyway, that is going to be it for most Fine Automata over the course of, this course. So we will use them more, especially when we get to regular expressions and whatnot. So NFAs will still have a lot of play there, especially with the regular operations like union and concatenation and whatnot. So we're going to touch on those eventually. But this really does kind of bring all the DFA versus NFA stuff to a head, essentially. So I hope all of that was helpful. Hope you learned something, and I'll see you in the next video.